All right, welcome to The Explainer. Today we're diving into a real cosmic head-scratcher. It's a mystery that's shaking up one of the fundamental laws of the universe, a rule that, honestly, astronomers thought they had totally nailed down.
Okay, so for decades, astronomers have had this beautifully simple rule called the baryonic-Tully-Fisher relation, or BTFR for short. You can think of it like a cosmic recipe, and it's super elegant. You just tell me how fast a galaxy is spinning, and this law, it tells me its total mass, all its stars and gas. Simple as that.
And when I say elegant, I really mean it. This thing is incredibly precise. The research itself calls it a remarkably tight correlation. What that means for us is that it's one of the most reliable tools we've ever had for measuring the cosmos. It just works. Or at least that's what we all thought.
So what's the problem? Well, it turns out that when we point our telescopes away from just single galaxies and start looking at the biggest things out there, these absolutely massive galaxy clusters, this perfect, super reliable law, it just seems to completely break down.
And this right here, this is the cosmic crime scene. That orange line, that's our individual galaxies, and you can see they're following the rule perfectly, just as expected. But then look at the blue line. Those are the giant galaxy clusters, and they are way off. I mean, they're following a parallel path, sure, but they are definitely not on the same line.
And we're not talking about a small gap here. It's a massive logarithmic offset of 0.6 to 0.8 decs. Now, to put that in perspective, in cosmic terms, that means the clusters are off by a factor of 4 to 6. That's a gigantic discrepancy, and it's had scientists scratching their heads for years.
This was so weird, so profound, that it forced astronomers to ask a really radical question. Like, are we looking at two completely different sets of physical laws? Is there one rule book for galaxies and a totally separate one for the colossal clusters they live inside? It sounds crazy, right? But then, a groundbreaking new paper comes along. It suggests something even more mind-bending. The answer isn't that the law is broken. The law is fine. The problem is our assumption that the law is like a rule carved in stone, unchanging for all of eternity. What if the law itself evolves? What if that's the piece we've been missing?
So this idea comes from a really fascinating theory of quantum gravity called the nexus paradigm. And here's the core of it. It proposes that as the universe expands, as it stretches out over billions of years, the effective strength of gravity actually gets weaker over time. Think about that. The fundamental rules themselves are evolving with the cosmos.
And this leads them to a brand new, time-dependent version of the equation. Now look closely here. The classic relationship between mass and velocity is still there, you can see it. But now there's this crucial third ingredient. See that little t? That's for time. The age of the object you're looking at fundamentally changes the entire calculation. Okay, so to really get our heads around why time is the secret ingredient here, let's try an analogy. It makes this whole evolving law thing much more intuitive. Let's imagine this physical law is like a currency exchange rate. Right, so stick with me here. The law is the exchange rate between a galaxy's mass and its speed. But here's the twist. That rate isn't fixed. It changes over time, kind of like economic inflation but driven by cosmic expansion. Galaxies are old. They bought their mass billions of years ago at an ancient exchange rate. Clusters are young. They bought theirs much more recently at the modern rate. So comparing them without adjusting for when they were formed, it's like comparing prices from, say, 1925 to today and being shocked that they're different. Of course they are.
And we actually have really strong evidence for this difference in age. When we look out into the universe, we're looking back in time, and observations show that galaxies are ancient. They formed way back when the universe was young, about 10.2 billion years ago. Galaxy clusters, though, they're the new kids on the block, cosmically speaking. They formed much more recently, only about 5 billion years ago.
So that creates this staggering age gap between them of 5.2 billion years. And you can bet that over 5 billion years, that cosmic exchange rate had plenty of time to change.
Which, of course, leads us to the ultimate question. Could this be it? Could this 5.2 billion year age gap be the smoking gun we've been looking for? Is time the one thing that solves this whole mystery? And this is where it all just clicks into place. You take that new, evolving equation, you plug in that 5.2 billion year time difference, and it predicts an offset of 0.65 decs. And that number? It lands perfectly smack dab in the middle of the observed mystery gap of 0.6 to 0.8 decs. The math just works
It's beautiful.
I mean, this isn't just a close enough guess. It's a direct hit. The theory doesn't just say, oh, there should be a gap. It predicts the exact size of the gap with incredible precision. And it does it using nothing but the age difference between galaxies and clusters. No special tricks.
So, what this all means is, well, it's truly revolutionary. We don't need two separate, confusing laws anymore. What we have instead is one single, elegant, universal rule that works for everything, from the tiniest dwarf galaxies all the way up to the most massive clusters in the universe.
What we're looking at now is a completely unified picture of the cosmos. Remember those two lines, the orange one and the blue one? Turns out they aren't describing two different rules at all. They're showing us the exact same rule, just viewed from two different points in cosmic history.
And this new model just shines where other big theories have really struggled. The standard model of cosmology, it can't explain this offset. Modified gravity theories like MOND, they get the slope right, but they also fail on the offset. But this new idea, it nails everything. It gets the slope, the scatter, and the cluster offset. And what's amazing is it does it all without needing any special tweaks or fine-tuning.
And that leaves us with one last, really provocative thought. One that could totally reshape how we see the universe. If a law this fundamental can change and evolve over time, what else can? What other constants of nature that we've built all our physics on are actually quietly changing as the universe gets older?